April 15th, 1945. Doberitz radar station, 30 kilometers northwest of Berlin. The Würzburg-Riese radar antenna rotated slowly against the pre-dawn darkness, its massive dish casting shadows across the concrete bunker below. Inside the cramped control room, Obergefreiter Klaus Zimmermann stared at his cathode ray tube display with growing unease. The green phosphorescent blips that had once revealed enemy aircraft formations with crystalline clarity now flickered erratically across his screen, appearing and vanishing like ghosts in the electronic ether. For 3 years, Zimmermann had operated Germany's most advanced radar equipment, tracking Allied bomber formations as they approached the Reich's industrial heartland. He understood the rhythm of air warfare, the predictable patterns of approaching B-17 flying fortresses and B-24 liberators. But tonight, something fundamental had changed. The aircraft signatures appeared impossibly faint, dissolving into static whenever he attempted to establish a tracking solution. Across the bunker, Hauptmann Werner Hoffmann reviewed the evening's intercept reports with mounting frustration. His Freya early warning radar had detected massive formations approaching from the west, yet his precision-guided Würzburg systems could not maintain consistent contact. The bombers seemed to materialize from nothingness, strike their targets with devastating accuracy, then vanish again into the electronic void. German night fighters scrambled to intercept phantom formations while real bombers delivered their payloads unopposed. What Hoffmann and his radar operators could not fully comprehend was that they were witnessing the culmination of an invisible technological revolution that had been developing since 1943. The Allied bombers approaching German airspace were no longer merely aircraft laden with explosives, become platforms for sophisticated electronic warfare systems that render them increasingly obsolete. The transformation began with a deceptively simple innovation called window, known to American forces as Chaff. These metallized paper strips, each precisely cut to half the wavelength of German radar frequencies, created false echoes that multiplied across radar screens like electronic snow. When deployed in sufficient quantities, window transformed orderly radar displays into chaotic storms of false returns, making it impossible for operators to distinguish genuine aircraft signatures from counterfeit reflections. The physics behind this deception were elegant in their simplicity. German radar systems operated by transmitting radio waves that reflected off metallic objects and returned to receiving antennas. The time delay between transmission and reception allowed operators to calculate target distance, while the strength of the return signal indicated aircraft size and composition. Window exploited this fundamental principle by creating thousands of false targets that appeared identical to genuine aircraft on radar displays. British scientists at the Telecommunications Research Establishment had developed window in 1942, but Allied commanders initially hesitated to deploy it. They feared that German forces would quickly copy the technology and use it against Allied radar systems. This concern proved prophetic, as German engineers did attempt to replicate Allied countermeasures once they understood the underlying principles. However, by the time Germany began producing its own Chaff, designated Duple, Allied electronic warfare capabilities had evolved far beyond simple radar reflection. The first major deployment of window occurred during Operation Gomorrah, the devastating bombing campaign against Hamburg in July 1943. British bombers released over 90 million chaff strips during the raids, completely saturating German radar frequencies and rendering the city's air defenses nearly blind. Radar operators reported seeing formations of aircraft that numbered in the thousands, far exceeding any actual bomber stream. German night fighters flew intercept missions against formations that existed only as electronic phantoms, while real bombers struck their targets with minimal interference. The psychological impact on German radar personnel proved as devastating as the physical destruction of Hamburg. Operators who had spent months mastering complex detection procedures suddenly found their expertise rendered worthless by clouds of metallized paper. Training programs that had emphasized precision tracking and fire control coordination became obsolete overnight as radar screens filled with indecipherable clutter. American forces expanded upon British innovations with characteristic industrial thoroughness. The 8th Air Force developed comprehensive electronic warfare packages that integrated multiple countermeasure systems into coordinated deception operations. B-24 Liberators were modified to carry carpet jammers, powerful transmitters that flooded German radar frequencies with electronic noise. These specialized aircraft, nicknamed jamming birds by their crews, accompanied bomber formations specifically to blind enemy detection systems. The carpet system represented a significant advancement over passive countermeasures like window. Rather than simply creating false targets, carpet actively disrupted radar reception by overwhelming German frequencies with broadband interference. Operators attempting to track approaching formations found their displays consumed by rolling waves of electronic static that obliterated all genuine returns. The system proved so effective that German radar personnel often remained unaware of bombing raids until explosions began falling on their targets. Operation Mandrel, implemented in early 1944, demonstrated the sophistication of Allied electronic warfare doctrine. Specially equipped aircraft flew patterns designed to create false bomber formations on German radar screens, while actual striking forces approached from entirely different directions. German controllers dispatched night fighters and activated flak batteries to defend against phantom threats, while real bombers devastated unprotected industrial targets. The deception extended beyond simple radar jamming to encompass comprehensive communication disruption. Operation Corona employed German-speaking personnel who intercepted Luftwaffe radio frequencies and issued false instructions to night fighter pilots. Confused aircrew received conflicting orders, incorrect vectors, and fabricated intelligence that led them away from genuine targets. The psychological warfare component proved particularly effective, as German pilots lost confidence in their ground control systems and began questioning all radio communications. German engineers struggled desperately to counter these evolving threats through technological innovation. The Telefunken Company developed frequency-agile radar systems that could rapidly switch between multiple operating bands, hoping to find clear frequencies unaffected by Allied jamming. Siemens produced improved signal processing equipment designed to filter genuine returns from chaff and electronic interference. The Würzburg-Riese system received upgrades intended to maintain tracking capability despite countermeasure deployment. Dr. Hans Hollmann, one of Germany's most brilliant radar engineers, led research efforts to develop anti-jamming technologies at the GEMA Company facilities. His team investigated pulse compression techniques, frequency diversity systems, and adaptive filtering methods that might restore German detection capabilities. However, these sophisticated solutions required resources and manufacturing capacity that Germany could no longer provide as Allied bombing intensified and raw materials became scarce. The Klein Heidelberg passive radar system represented Germany's most innovative attempt to overcome Allied electronic warfare. Rather than transmitting its own signals, Klein Heidelberg detected aircraft by analyzing reflections from British radar transmissions. The system exploited the fact that RAF chain home stations continued operating throughout the war, providing a constant source of illumination that German receivers could monitor. Aircraft flying between German listening posts and British transmitters created shadows and reflections that revealed their presence without requiring active German radar emissions. While technically ingenious, Klein Heidelberg arrived too late and in insufficient quantities to meaningfully impact the air war. Only a handful of installations became operational before Germany's surrender, and their limited coverage provided minimal protection against the massive bomber formations that darkened German skies daily. The system's development highlighted the fundamental problem facing German technology by 1945. Brilliant individual innovations could not compensate for systemic industrial collapse and resource exhaustion. By winter 1944, German radar operators had developed informal methods for attempting to track Allied aircraft through electronic interference. Experienced personnel learned to recognize subtle patterns in chaff deployment that might indicate genuine bomber formations. They studied timing sequences, signal strength variations, and frequency characteristics that sometimes revealed authentic targets hidden among false returns. However, these techniques required exceptional skill and provided inconsistent results under combat conditions. The human cost of radar warfare remained largely invisible to contemporary observers, but proved devastating for German air defense personnel. Operators worked extended shifts in cramped, poorly ventilated bunkers, straining to interpret degraded displays under constant pressure. The psychological stress of failing to detect incoming raids, combined with the physical effects of prolonged exposure to electronic equipment, created casualties that never appeared in official statistics. As 1945 progressed and Allied forces approached German borders, radar stations faced direct ground attack in addition to electronic warfare. Many installations were destroyed by advancing armies, while others were abandoned as their positions became untenable. The sophisticated detection network that had once protected German airspace dissolved into isolated outposts operating obsolete equipment with minimal coordination. The final irony of Germany's radar collapse became apparent through post-war intelligence assessments. German scientists had pioneered radar technology in the 1930s, developing systems that provided tactical advantages throughout the war's early phases. Their innovations in antenna design, signal processing, and fire control integration had established Germany as the world leader in radar applications. Yet by 1945, this same technological superiority had become a strategic liability as Allied forces turned German radar expertise against itself through sophisticated countermeasures and electronic deception. The technical revolution sweeping across German radar installations demanded immediate countermeasures that stretched engineering capabilities to their absolute limits. At the Telefunken research facility in Berlin, Dr. Wilhelm Runge assembled teams of scientists working around the clock to develop frequency-hopping radar systems that could outmaneuver Allied jamming. The concept appeared theoretically sound. If German radars could rapidly switch between multiple operating frequencies, they might find clear channels unaffected by enemy interference. Yet practical implementation revealed the staggering complexity of frequency-agile systems. Each radar installation required sophisticated switching mechanisms, multiple transmitter modules, and coordination systems that demanded precision manufacturing far beyond Germany's diminishing industrial capacity. The Würzburg-Riese installations needed complete rebuilding to accommodate frequency diversity, requiring resources that simply no longer existed as Allied bombing campaigns systematically destroyed German production facilities. Meanwhile, at the Siemens facilities in Munich, engineers pursued an entirely different approach through improved signal processing. Dr. Ernst Kramer's team developed filtering algorithms designed to distinguish genuine aircraft returns from chaff interference by analyzing signal characteristics and movement patterns. Their research identified subtle differences between authentic radar echoes and false returns created by metallized strips, differences that might allow experienced operators to track real bombers through electronic clutter. The filtering systems showed promise during laboratory testing, correctly identifying aircraft signatures in controlled conditions with simulated interference. However, combat deployment revealed insurmountable limitations. The processing equipment required to implement advanced filtering consumed enormous amounts of electrical power, demanded constant maintenance by highly trained technicians, and proved unreliable under the harsh conditions of operational radar sites. Most critically, the systems could not function effectively when faced with the massive scale of chaff deployment that characterized major Allied bombing raids. American electronic warfare specialists had recognized that overwhelming German radar capacity through sheer volume represented the most effective approach to neutralizing enemy defenses. Rather than relying on sophisticated deception techniques, they deployed countermeasures on such an enormous scale that German systems simply could not process the incoming data. A single B-24 Liberator carrying maximum chaff loads could generate thousands of false targets simultaneously, effectively multiplying its radar signature by factors of 10,000 or more. The mathematical reality proved devastating for German operators. When faced with displays showing tens of thousands of potential targets, human controllers could not possibly coordinate effective intercepts even if they successfully identified genuine aircraft among the false returns. The cognitive overload created by massive Chaff deployment paralyzed German air defense networks as effectively as complete radar failure, perhaps more so because operators continued attempting to track formations that existed primarily as electronic phantoms. Dr. Hans Hollmann's team at Gema made one final attempt to overcome Allied countermeasures through revolutionary passive detection methods. The Klein Heidelberg system represented a fundamental departure from traditional radar principles, abandoning active transmission entirely in favor of analyzing reflections from existing electromagnetic sources. British chain-home radar stations, operating continuously throughout the war, provided ideal illumination for passive detection systems that could monitor aircraft shadows and reflections without revealing their own positions. The passive radar concept offered theoretical advantages that seemed to address every weakness of conventional systems. Klein Heidelberg installations could not be jammed because they transmitted no signals for Allied equipment to interfere with. They remained invisible to enemy direction-finding equipment because they operated purely as receivers. Most importantly, they exploited Allied radar transmissions as their primary detection medium, turning British technological advantages against themselves through ingenious technical jiu-jitsu. Initial testing at the Peenemünde facility demonstrated Klein Heidelberg's remarkable capabilities under ideal conditions. The system successfully tracked aircraft at ranges exceeding 200 kilometers by analyzing minute variations in reflected British radar signals. Test flights using captured Allied aircraft confirmed that passive detection could maintain continuous tracking even when active German radar systems lost contact due to electronic interference. Yet Klein Heidelberg arrived at a moment when Germany lacked the industrial infrastructure necessary for widespread deployment. The system required precision receivers, sophisticated signal processing equipment, and extensive antenna arrays that demanded manufacturing capabilities that no longer existed. By late 1944, German electronics production had collapsed under relentless Allied bombing, leaving innovative designs stranded in laboratory prototypes that could never reach operational deployment. The few Klein Heidelberg installations that achieved operational status provided tantalizing glimpses of what might have been possible under different circumstances. Operators reported successful detection of Allied formations during conditions when conventional radar systems showed only electronic noise. The passive approach proved particularly effective against electronic warfare aircraft that concentrated their jamming on active German frequencies, while remaining vulnerable to passive detection methods that exploited British transmissions. However, even successful detections could not translate into effective intercepts given the broader collapse of German air defense coordination. Klein Heidelberg stations that identified incoming bomber formations often could not communicate their findings to night fighter units or flak batteries, because Allied jamming had disrupted German communication networks. The system's technical brilliance became strategically irrelevant when embedded within a broader defense network that had lost the ability to coordinate effective responses. American intelligence officers conducting post-war assessments recognized Klein Heidelberg as the most sophisticated radar innovation developed by any combatant during the conflict. Technical evaluation teams that examined captured installations reported detection capabilities that exceeded many contemporary Allied systems, achieved through engineering principles that would influence radar development for decades. The passive detection concept, pioneered by German scientists, became fundamental to modern electronic warfare doctrine and stealth aircraft development programs. The human drama unfolding within German radar installations during the final months of the war reflected broader themes of technological obsolescence and strategic desperation. Obergefreiter Klaus Zimmermann and of operators thousands like him had spent years mastering complex detection procedures that suddenly became worthless against evolving Allied countermeasures. Their expertise, accumulated through months of training and combat experience, could not compensate for fundamental shifts in the electromagnetic battlefield that rendered traditional radar doctrine obsolete. Training programs hastily implemented to address electronic warfare threats proved inadequate for the scale and sophistication of Allied jamming operations. New operators arriving at radar stations received instruction on equipment and procedures that were already obsolete by the time they reached operational deployment. Veteran personnel who understood the subtleties of radar interpretation found their knowledge increasingly irrelevant as displays filled with interference that no amount of skill could penetrate. The psychological toll on radar personnel intensified as German cities burned under bombing raids that their systems had failed to detect. Operators watched helplessly as Allied formations approached undetected, delivered devastating attacks, and departed without meaningful interference from defenses they were responsible for coordinating. The weight of professional failure combined with personal danger as radar installations became priority targets for Allied fighter bombers and artillery. Medical reports from German radar installations documented increasing rates of nervous exhaustion, eye strain, and stress-related disorders among personnel working extended shifts under impossible conditions. The physical demands of operating complex electronic equipment during air raids, combined with the psychological pressure of repeated operational failures, created casualty rates that never appeared in official statistics, but decimated the experienced personnel necessary for effective radar operations. Administrative documents recovered after the war revealed the extent to which German radar effectiveness had collapsed by early 1945. Monthly reports from radar stations across the Reich documented dramatic reductions in successful intercepts, with many installations reporting weeks without confirmed detection of enemy formations. The precision-guided air defense system that had once protected German industrial targets had degraded into isolated outposts operating obsolete equipment with minimal coordination or effectiveness. By March 1945, as Allied forces crossed the Rhine and Soviet armies approached Berlin, many radar installations were abandoned or destroyed by their own crews to prevent capture. The sophisticated German technological super-id detection network that had representationality dissolved into scattered remnants operating sporadically until communication systems failed entirely. The electronic shield that had once protected the Reich had become as ghostly and insubstantial as the phantom formations that filled German radar screens throughout the war's final months. The irony was not lost on German scientists who had pioneered radar technology in the 1930s, only to watch their innovations turned against them through superior Allied electronic warfare capabilities. Their technical achievements had enabled early German military successes, providing the detection and coordination systems necessary for effective air defense and night fighter operations. Yet these same innovations became strategic vulnerabilities as Allied forces developed countermeasures that exploited the fundamental physics underlying radar detection principles. The Reich's scientific community faced a sobering reality that transcended individual technical failures. Dr. Wilhelm Runge, directing radar development at Telefunken, received intelligence reports throughout late 1944 that painted an increasingly desperate picture. Allied bombing formations were penetrating German airspace with virtual impunity, their electronic warfare capabilities evolving faster than German countermeasures could be developed or deployed. The captured Allied equipment told a story of industrial coordination that German engineers found both impressive and terrifying. American jamming transmitters bore manufacturing stamps from dozens of companies, indicating a production network that could rapidly scale electronic warfare equipment across thousands of aircraft. German factories, struggling to produce basic components under constant air attack, but fundamental transformation of aerial this level of systematic manufacturing integration and British had recognized. Intelligence, then German commanders that control merely tactical innovation, combat doctrine. The Americans earlier could not match assessed electronic warfare representments revealed that alley of the electromagnetic spectrum would determine air superiority more decisively than aircraft performance or pilot not skill. While German engineers focused on improving individual radar systems, Allied scientists developed comprehensive approaches to electronic dominance. The psychological warfare component proved particularly devastating to German morale. Operation Corona's German-speaking personnel infiltrated Luftwaffe communication networks with such sophistication that night confidence in their own fighter pilots lost ground control systems. Aircrew reported receiving contradictory vectors, false target information, and conflicting orders that led them away from genuine bomber formations, while Allied aircraft struck undefended targets. Captain Hans Müller, commanding a night fighter squadron based near Frankfurt, documented the operational chaos in his final mission reports. His pilots increasingly refused to follow radio instructions without visual confirmation, having been deceived repeatedly by false communications. The breakdown of trust between aircrew and ground controllers effectively paralyzed German night fighter operations even when radar systems functioned correctly. By February 1945, German radar installations operated in virtual isolation, their communication networks so thoroughly compromised that coordination between stations became impossible. Individual operators maintained lonely vigils, tracking formations they could not effectively report to higher commands or neighboring installations. The integrated air defense system that had once protected the Reich fragmented into scattered outposts operating independently with minimal strategic impact. The final months revealed the true scope of German technological defeat. American B-17 and B-24 formations approached German targets with electronic that render warfare packages to entire defense sectors blind and deaf simultaneously. Carpet jammers flooded radar frequencies with broadband interference, while Mandrel transmitters created false formations on surviving displays. German operators faced the impossible task of coordinating defenses against enemies they could neither see clearly nor communicate about effectively. Post-war interrogations of captured German radar personnel revealed the human cost of this technological collapse. Experienced operators described months of professional frustration as their expertise became increasingly irrelevant. Many reported psychological trauma from repeatedly failing to detect raids that devastated their own cities and families. The weight of technological obsolescence combined with personal loss created casualties that never appeared in official Wehrmacht statistics. The irony became apparent through captured German documents that revealed the sophistication of their theoretical understanding. German scientists had correctly analyzed Allied electronic warfare principles and developed countermeasures that might have proven effective under different circumstances. Their passive radar concepts, frequency-agile systems, and advanced signal processing represented innovations that influenced post-war radar development for decades. However, brilliant individual solutions could not overcome systematic industrial collapse. The same bombing campaigns that German radar was supposed to detect and counter had destroyed the manufacturing capacity necessary to produce effective countermeasures. German engineers found themselves in the impossible position of developing sophisticated solutions they lacked the resources to implement at meaningful scale. American technical intelligence teams that examined German radar installations after surrender reported equipment that impressed them with its theoretical sophistication. The Klein Heidelberg passive radar system demonstrated detection principles that Allied scientists had not considered. German signal processing innovations provided filtering capabilities that exceeded contemporary American systems in laboratory conditions. The electronic warfare revolution that began with simple metallized paper strips in 1943 had fundamentally transformed the nature of aerial combat by 1945. German radar operators who had once tracked enemy formations with mathematical precision found themselves staring at screens filled with electronic phantoms, their expertise rendered obsolete by innovations they could neither counter nor fully comprehend. The invisible war fought across radio frequencies had proven more decisive than any conventional battle, determining air superiority through electromagnetic dominance rather than aircraft performance or pilot skill. When Germany surrendered on May 8, 1945, Allied intelligence teams discovered the true scope of what they had accomplished. In bunkers and research facilities across the Reich, they found evidence of sophisticated German radar innovations that had arrived too late and in insufficient quantities to change the war's outcome. The Klein Heidelberg passive radar system, frequency-agile transmitters, and advanced signal processing equipment represented theoretical breakthroughs that would influence radar development for decades. Yet these brilliant solutions had been overwhelmed by the systematic application of industrial-scale electronic warfare that American and British forces had perfected. The lessons learned from this electromagnetic battlefield would reshape military thinking throughout the Cold War and beyond. The principle that controlling the electromagnetic spectrum could neutralize technological advantages became fundamental to modern warfare doctrine. American investment in stealth technology, beginning with radar cross-section research in the 1950s, represented the direct evolution of wartime electronic warfare concepts. The invisible bombers of 1945 had become the truly invisible aircraft of future generations. Dr. Hans Hollmann and his fellow German radar pioneers, interrogated by Allied technical intelligence teams, admitted what their wartime reports had carefully avoided stating. By 1945, they could no longer see the enemy at all. The electronic shield that had once protected the Reich had become as insubstantial as the phantom formations that filled their radar screens. They had mastered radar technology before anyone else, pioneering innovations that provided early tactical advantages. But in the end, they had been rendered blind by an enemy that understood something they had not. In modern warfare, the invisible battle fought across radio frequencies would determine victory more decisively than any conventional engagement. The war's final irony lay in the recognition that both sides had possessed the technical knowledge necessary for effective electronic warfare. The difference had been industrial capacity, systematic application, and the willingness to invest resources in unglamorous but decisive technologies. American factories had produced electronic warfare equipment on the same massive scale that characterized their aircraft and ammunition production. German scientists had developed brilliant individual solutions that could never be manufactured in quantities sufficient to matter. The radar war of World War II had quietly established principles that would govern aerial combat for generations. Control of the electromagnetic spectrum, rather than superiority in aircraft design or pilot training, had become the foundation of air dominance. The invisible frequencies that carried radar signals had proven as strategically important as the visible formations of bombers they were meant to detect. In the end, the war had been won not just through overwhelming industrial production, but through the systematic application of scientific innovation to render enemy technology obsolete.